Hello everyone, welcome to this lecture. So, for the next few lectures we will be now focusing on domain extension for perfectly secure broadcast. Earlier we had seen domain extension for Byzantine agreement, namely the domain extension by Turpin and Cohn, and at that time I promised that later on we will see more efficient domain extension protocol. So, we will now see the more efficient domain extension based on the properties of Reed-Solomon error correcting codes. So, we will start with the problem description, and before going into the exact protocol for domain extension, we will see some additional properties of Reed-Solomon error correcting codes which will be useful. Okay. So, what exactly is the goal of domain extension for broadcast and Byzantine agreement? So, we will be focusing on the domain extension for broadcast, but since the broadcast and Byzantine agreement problems are equivalent to each other in the honest majority setting, namely in the sense that a protocol for one problem implies protocol for other. So, you can imagine that if we have an efficient domain extension protocol for broadcast, then we can use it to get a domain extension protocol for Byzantine agreement as well. So, in the context of broadcast, the goal for domain extension is as follows. We have seen various bit broadcast protocols with n greater than 3t. Okay. Say for instance, the EIG protocol, the phase king protocol with the various communication complexities, and these are bit broadcast protocols where the sender's message is a single bit. Now, what if the input of the sender is from a bigger set? Say the sender's input is no longer is just a single bit, but rather it is a bit string of size L bits. So, there are two ways to achieve broadcast for L bits. One option is that we run any bit broadcast protocol L times, where the input for the ith instance of the bit broadcast will be the ith bit of the sender. Okay. And then the overall output for the parties will be the individual outcome, will be the concatenation of the individual outputs which the parties receive from the various instances of the bit broadcast, namely from the L instances of the bit broadcast. However, this will require a communication complexity which will be L times the communication cost of one instance of bit broadcast. So, this notation BC and within the parenthesis 1, it denotes the communication complexity for one instance of bit broadcast. Say for instance, if we are considering the EIG protocol, then BC1 for EIG protocol is n power t plus 1. That means, if we run L instances of the EIG protocol, the overall cost will be order of n power t plus 1 times L, whereas if we use the phase king protocol as the bit broadcast protocol, then the overall complexity will be order of n cube times L. Okay. The domain extension, which is the option number 2, is basically to design a broadcast protocol where the sender's input is now of size L bits, where the existing bit broadcast protocols are executed only a constant number of times independent of the size of L. Okay. And we had already seen earlier the Turpin-Cohn domain extension protocol. There the communication complexity of the overall broadcast protocol was this. Of course, we had seen the Turpin-Cohn domain extension in the context of Byzantine agreement, but as I said, the same extension will work even for the broadcast with the same complexity. So, now you can see that from the communication complexity expression, the cost which depends upon L, it is only over the point to point channel, namely this order of n square L bits of communication happens over the point to point channels, and existing bit broadcast protocols are executed only for a constant number of times, which is independent of L. Now, we will now see a more efficient domain extension protocol, where the overall communication complexity will turn out to be this much. Okay. So, now you can see that this is much better than Turpin-Cohn's protocol, and this communication complexity of order of NL plus the cost of bit broadcast will be asymptotically optimal. Communication wise, it will be asymptotically optimal. This is because if we substitute the cost of the bit broadcast, say by the phase king bit broadcast protocol, then the overall cost turns out to be order of n times L plus order of n cube. That means, if the message size small l is guaranteed to be say theta of n square, that means if you have a sufficiently large message, then this expression order of n l plus order of n cube will become order of n l, namely the term order of n cube, which is coming due to this constant number of invocations of the bit broadcast, will be asymptotically subsumed in this order notation we go of n l. That means, asymptotically I can claim that for sufficiently large L, the total cost will turn out to be order of n times L bits, because whatever is the additional term coming due to the bit broadcast instances will be subsumed asymptotically in this order of n l expression. Now, order of n l bits of communication is obviously an optimal communication complexity for any broadcast protocol, where the sender's message is of size L bits, because since it is a broadcast, it needs to be guaranteed that the sender's message is communicated to all the parties at least once. Of course, in the protocol the parties may exchange messages further, but in order that every party obtains the sender message, the sender has to send its message to every other party, and that trivially requires a communication complexity of order of n l, sorry omega of n l. That is a minimum communication required in any broadcast protocol where the sender's message is of size L bits. And what is the total communication complexity we will be achieving through the more efficient domain extension broadcast protocol? That will be order of n l. That means, we will be asymptotically achieving the minimum cost which is expected from any broadcast protocol for message size of L bits. Okay. So, before going into our exact domain extension protocol, we need to understand some more properties of Reed-Solomon error correcting codes. So, just to recap, this is the Reed-Solomon encoding algorithm, where if the sender has a message consisting of k elements, namely consisting of k symbols from the field k, then to compute the Reed-Solomon code word, a message encoding polynomial f sub m x is formed, which is a k minus 1 degree polynomial with coefficients being m naught, m 1, m sub k minus 1, and then that polynomial is evaluated at n publicly known values alpha 1, alpha 2, alpha I, alpha n, and they constitute the individual components of the code word. That is a Reed-Solomon encoding algorithm. Now, the first property that we require later in our domain extension protocol is the following. Any k components of this code word vector uniquely determine the remaining components of the code word vector. That means, you do not need the full code word vector to identify what exactly was the sender's message. Even if I give you any k components of this code word vector, and those k components need not be the consecutive k components, they could be any subset of the k components of this full vector. That will be sufficient to determine the remaining components of the code word. So, for demonstration, imagine that I give you say the first k components, but as I said, whatever I am claiming here holds for any k component. So, imagine you are given only the k components of the code word, and you are not given the remaining components, they are unknown for you. Of course, you know the value of alpha 1, alpha 2, alpha I, alpha n, because they are publicly known, and you do not know the value of the underlying polynomial, underlying message encoding polynomial. But what you know is that the components which are given to you, they are basically the value of the so called message encoding polynomial at the corresponding alpha points. That is what is known to you. Now, the k components which are given to you basically constitute k distinct points on the polynomial f sub m, namely the message encoding polynomial. And what was the degree of the message encoding polynomial? Well, it is a k minus 1 degree polynomial. That information is available to you, what is the degree, because that is a system parameter. Now, you are given k distinct points on a k minus 1 degree polynomial, and recall that we know from Lagrange's interpolation that any k distinct points on an unknown k minus 1 degree polynomial are sufficient to uniquely determine that unknown polynomial. So, through the components which are given to you, the k components, you can interpolate the message encoding polynomial, and once you encode you can compute the message encoding polynomial, and once the message encoding polynomial is computed, well, you can evaluate it at the remaining alpha values to find out what were the missing components, that is all, right. So, we will be extensively using this property. That means, it is not necessary to know this full vector of size n to determine the message encoding polynomial or the message which was the input for the Reed-Solomon encoding algorithm. Any k components, knowledge of any k components is sufficient. Now, let us see some more properties. The next property that we will be using later is the following. If you are given two Reed-Solomon code words corresponding to two messages, and if it so happens that the two Reed-Solomon code words have the same number of components have the same k or more number of components, okay, then both the code words correspond to the same message, and they are actually the same code words, they are not the different code words. So, what I am saying here is the following. So, imagine you are given this code word whose components are C11, C12, C1k, C1n, and you are given another code word, Reed-Solomon code word whose components are C21, C22, C2k, C2n. Now, imagine that the first code word corresponds to a message where the underlying message encoding polynomial is a k minus 1 degree polynomial with coefficients being m sub 1 0, m sub 1 1, m sub 1 k minus 1. That means, the first message that means this polynomial corresponds to a message m, and say the components of the message are m sub 1 0, m sub 1 1 up to m sub 1 k minus 1. If that is the case, then the message encoding polynomial would have been f sub 1 x polynomial, and the components of the code word would have been the evaluation of this polynomial f sub 1 at x equal to alpha 1, alpha 2, alpha k, alpha. In the same way, imagine that The second code word is obtained by evaluating a message encoding polynomial whose components are m sub 2 0, m sub 2 1, m sub 2 k minus 1. Namely, it corresponds to a message m prime whose blocks are m sub 2 0, m sub 2 1, and like that m sub 2 k minus 1. Again, component wise, the code components of this second code word will be the evaluation of the second polynomial f sub 2 x at x equal to alpha 1, alpha 2, alpha k, alpha n. Now, imagine that these two code words have the same k or greater number of components. Say for simplicity, both these two code words have the first k components being the same. Okay, they have the same first k components. That means, the first component of the first code word C11 is same as the first component of the second code word, and like that the kth component of the first code word is same as the kth component of the second code word. Now, this equality means that f1 of x and f2 of x have at least k common values. Why at least k common values? Because each of these values are individually k distinct points on polynomials f1 of x and f2 of x respectively, and since they are equal, that means both the points both these two polynomials f1 x and f2 x give you the same value at k number of alpha distinct alpha values. But what was the degree of f1 of x and f2 of x? Both of them are k minus 1 degree polynomial, and we know that two different k minus 1 degree polynomial can have at most k minus 1 number of common values. That means, if at all the two messages m and m prime are different, then only up to k minus 1 points on the polynomials f1 of x and f2 of x could be common. That means, the code words corresponding to message m and m prime would have been would be same at most k minus 1 locations, but we are given that they have the same components at k or more number of locations. That automatically implies that the polynomials f sub 1 x is same as the polynomial f sub 2 x, and f sub 1 x basically corresponds to the message m, and f 2 sub x corresponds to the message m prime, which automatically implies that m is equal to m prime. Okay. I stress here, when I say that the two code words have the same number of k or greater number of components, that means they have to be at the same location. So, you have seen here that the first component of both the code words are same, the second component of both the code words are same, and so on. Okay. So, that is the second property of the Reed-Solomon error correcting codes, which will be useful later when we discuss the exact domain extension protocol. Namely, two different RS code words corresponding to messages of size k can have at most k minus 1 common components. They can't have more, they can't have k or more number of common components. So, these are the references which are used for today's lecture. The domain extension based on the properties of Reed-Solomon error correcting codes were first studied in this paper, and then a more efficient version of the protocol was proposed in this follow up work. Thank you.